Welcome to Lecture 3. We have finished our lectures 1 and 2 last week, where we looked at scientific notation, significant figures, and doing some unit conversions. We are going to continue with the math. The whole second half of the semester is the math of introductory chemistry, and we're going to introduce the mole today. So Lecture 3 involves introducing Avogadro's number, the concept of molar mass, and we're going to revisit chemical formulas, which we've already done quite a bit with in the first half of the course. We're just going to revisit that very shortly, very small amount of time spent on that. So we've learned a lot about the periodic table and formulas, but we have not learned how to count particles. And so we are going to learn that Avogadro's number, which is a very big number, but it's still a number. It's a scientific notation number. But we're going to use it as a conversion factor to go between our counting unit in chemistry, which is the mole, and numbers of particles. Now, there are a lot of things that are counted by different counting units, and I've got a few examples here in the notes. Nails are counted by weight. You usually buy them by the pound. Mardi Gras beads are still sold in gross units, which is a very old English counting unit. Copy paper is sold in what's called a ream, which is 500 sheets in a package. So I've got a little problem here. What is the mass of 1,500 sheets of paper, standard printer paper? And if one ream has 500 sheets and weighs 2.03 kilograms. Now you can probably do this, most of you, very quickly because it doesn't involve anything that's totally weird. So 1,500 sheets is 3 reams, and each ream weighs 2.03 kilograms. But we really do need to use our converting, doing the units the same way we learned in the first 2 lectures if we're going to be successful in doing these types of conversions as well. So I'm bringing this over where I can write, and so we have 1,500 sheets of paper. Even though I know you can do this without doing this, I'm reinforcing this way of solving problems by using the units. It is 2.03 kilograms for every ream or for 500 sheets. Now you could do it this way, and it's just one conversion, and you've got it. All right? Or you could do 1,500 sheets times 1 ream is 500 sheets, and I had to put the sheets on the bottom to get that unit to cancel, and then times 2.03 kilograms per ream. So you're doing the same thing. You're just, in this first example up here, you are making that substitution automatically. But this is the way we need to be working these problems. So the answer to this is 1,500 divided by 500, which is 3, times the 2.03, which 6.09 kilograms should be the right answer for that. All right, so we're going to be doing more of this. We're going to be doing it for the rest of the semester, essentially, as we've put the math off to give you more time to learn the language of chemistry first before we focus on the math. All right, back to the notes. Eggs are sold by the dozen, and we're going to use eggs today to introduce you to this counting unit, which is the mole. That's our counting unit in chemistry. How many things are in a mole? Avogadro's number. All right, so we're going to look at eggs to get us started because eggs are very familiar to you. And I am going to introduce what I call the chart. Okay, and so what I'm going to do is take all of this into a little notebook program, and we're going to work through these examples so that you can then seamlessly transport this to the mole. All right, so we're going to undo writing. Can I do that? Oh, just a little bit at a time. I really just want to clear this. Let's see. We'll just erase. Okay, and then we'll put in what I just brought in. All right, you need your calculator. All right, if you don't have that, and you're going to need a periodic table, so go ahead and get that out. Because as we move from eggs into the mole, we'll be needing the calculator. All right. So what I have here is a chart, okay, where we are going to be doing, let me change that orientation. Okay, where we are going to talk about the conversion factor to go back and forth between dozens and eggs, and the conversion factor to go back and forth between mass and dozens. And exactly the same type, where we multiply here with the eggs example, we're going to be multiplying with the mole example, and so forth. So it's a really good way to introduce this idea of a chart as a map, a road map to how to do the problems. You should, of course, use the units, and I will be doing both. So let's go ahead and get started. One thing that was in the notes was that on average, 1 dozen eggs weighs 70 grams. So 1 dozen eggs has a mass of 70 grams. Now that is not going to be true when we get to particles. They don't all have the same mass. But the idea of how we're going to deal with mass is the same. 70 grams, not kilograms. All right, so what we're going to do with the chart is we're not going to put the answers to these questions. We'll write those underneath, but we're going to put the mathematical operation in the chart. So first question, how many eggs in 2 dozen? You don't even have to think about this. You know it's 24. Because what you have done is you have in your head, because eggs are so familiar to you, you have multiplied the number of dozens times 12. All right? So 24 was our answer. All right. So times 12, 12 eggs per dozen. How many dozen is 36 eggs? So you're starting here now. And I know that automatically in your head you knew that it was 3, but what you did in your head was you divided by 12. If only I could always understand what's going on in your heads. So when I go back and forth between dozens and eggs, I am multiplying by 12 in one direction, dividing by 12 in another. We're going to be doing exactly the same thing when we get to the mole. Our number just won't be 12. It's going to be Avogadro's number. But we'll get there in a minute. Now, moving to the other side of the chart. So just like it will be for moles, the right-hand side of the chart is for numbers of particles, or in this case, numbers of eggs. Has nothing to do with mass. The other side of the chart is going to be all about mass. And the same thing will be true when we get to the mole. So one side of the chart, you're going to use Avogadro's number. The other side of the chart, when we get to moles, is going to be the periodic table. So let's do eggs first. Number 3, what is the, all right, so we didn't answer our question here. That was 3. Number 3, what is the mass of 2 dozen eggs? So we're going to use this fact to answer that question. So I take my numbers of dozen and I multiply times 70. Okay? To get what is the mass of 2 dozen eggs, 70 times 2, that's 140 grams. So that's pretty easy. And then the next question is the reverse of that. How many dozen is 210 grams of eggs? So remember that grams is mass. And if I'm going to get to my central counting unit, which for eggs is the dozen, I'm going to divide that mass by 70. Because each dozen weighs 70. So dimensional analysis, unit-wise, I'm taking 210 eggs. And this is my conversion factor. And I want to get rid of eggs. So it is, I don't want dozens, so 1 dozen, not 210 eggs, 210 grams. Okay, get our units right. 210 grams of eggs times 1 dozen is 70 grams. And that's what I'm doing. You're going to be doing the same thing when you get to moles. So the answer to that is 3. Because 210 divided by 70 is 3. Now the next question is, how many eggs is in 210 eggs? Now you can go back, in 210 grams of eggs. You could go back here, do that same operation you did in number 4, and then you're going to multiply by 12 to get that answer. But you've already got the answer to number 4. It's 3. So 3 times 12 is 36. So you started here on number 4. And the first question, number 4, was to get to here, divided by 70. The next question was how many eggs? going in this direction, you are multiplying by the number of eggs in a dozen. You are going to do the same kinds of operations when we do the mole. All right, so I'm going to get ready for that by putting in a blank page. There we go. And then we'll go back to the notes to continue on. Now we did miss one more little step here, so let's just do it without me bringing it into the writing program. What is the mass of 400 eggs? So where are you starting on the chart? And where are you going? You are starting, let me just bring the chart up here in the notes. You are starting with eggs, numbers of eggs. And in order to get to mass, you've got to do two operations. You've got to go to dozens, and then you're going to go to mass. All right? So 400, I'm going to talk you through it. Get your calculators. 400 eggs. I got to get to the central counting unit. You're going to do the same thing with the mole. 400 divided by 12 to get the number of dozen. Then multiply times how much a dozen weighs. And your answer should be 2,330 grams. Or in scientific notation, 2.33 times 10 to the third grams of eggs. All right, so the chart is a roadmap. I provide it for students at this level who need a little bit more of a visual orientation to doing this kind of thing, instead of just doing the dimensional analysis. All right, now we're going to convert the chart to a chemistry chart. The number of eggs becomes particles. Now this is very important, and I will write it on when I get to the writing program. Particle is a general term. It can be atoms, if the substance is made up of atoms, and that's most elements. You know the 7 that are not made up of elements, and they come 2 at a time. Don't forget your language. Molecules, particles can be molecules if the substance is covalently bonded, nonmetal, nonmetal. So this is where knowing more about the language is going to help, I think, with the math. Or we call ionic compounds formula units. We don't call them molecules. They're not molecular. So particle is a generic word. So eggs becomes particles. Dozens becomes moles. Okay. The mathematical operations and everything is going to be the same, but instead of 12, we're going to use Avogadro's number, which is this scientific notation number here. 6.02 times 10 to the 23rd. Of course, mass is still mass, but the mass of 1 mole will not be constant as it was for eggs. It's going to be from the periodic table. So I am going to take, I'm going to draw the mole chart when we get there, and we are going to do these conversions right here. So let me just take those and copy them. That's like that. All right, we're going to do these first two, then we're going to talk about molar mass, and then we'll finish the chart. Okay, so bring it back to. All right. So first thing I'm going to do before I put those questions in is draw the chart. So mass is still mass. Instead of dozens, we have the mole. Now, you will see it in the book, the E dropped off often. I'll put the E on here. Particles. So nothing has changed really except for the central counting unit and the numbers we're going to use to go back and forth. All right, so this part of the chart, the right-hand side of the chart, is a constant. What you're multiplying and dividing by, same operations apply as with eggs, but you're going to use Avogadro's number. So I'm going to put Avogadro's number, okay, and we'll write it off to the side. 6.02 times 10 to the 23rd particles per mole. All right. Going back and forth between our central unit and mass, we are going to use the periodic table, the PT. All right. And what's on the PT is how much a mole weighs. It is the molar mass. If it's an element, then you can read it right off the table. If it is a compound, then we're going to have to add those molar masses up. So the units for molar mass are grams per mole. Okay, now I'm ready to copy those questions in and bring them down. All right, so full screen since it's easier to see. There we go. All right, so we're going to answer these questions. We're going to do the same calculations we did with eggs. We're just using different numbers. So how many atoms, so that's a particle word, are in 2 moles of copper? So we are starting here with in the middle with the mole, and we're going to particles. It really doesn't matter in A, B, or C what it is. But we're always going to tell you what it is, but it's not going to matter. 2 moles times Avogadro's number, it doesn't matter if it's copper, hydrogen sulfide, or sodium chloride. It doesn't matter. But we're going to do the same operation. There are going to be some instances where we're going to take things apart, and then the numbers and the formulas do matter. All right, so anyway, 2 times Avogadro's number. Now here you're going to get some more experience with doing scientific notation on your calculator. Okay, so when you take and multiply those two, you should get 1.20 times 10 to the 24th particles. In this case, it's atoms. So as part of learning the language some more, you know that if you're dealing with an element like copper, that the particle is going to be called an atom. Again, generic word, can be atoms, molecules, it can also be ions, formula units. Okay? All right. So, pretty easy. Part B, how many molecules? So I'm going to use what I'm doing here in A, B, and C is introducing you to all the particle words. So hydrogen sulfide, nonmetal, is made up of molecules. Now I should be putting in my units here. 6.02 times 10 to the 23rd for this substance, molecules per mole. And of course this is mole, so those moles cancel out and you end up with your molecules. So on your calculators, 3 times 6.02, and you will see it written as 6.022. Either way you can use. I usually just use 6.02. 1.81. Now, I was only given 3.0, and remember we don't use the significant figures from any kind of conversion, so really it should be just 1 decimal place, 1.8 times 10 to the 24th molecules. Right? Because that is what hydrogen sulfide is made up of. And then last, how many formula units in 10 moles of sodium chloride? Because that's an ionic compound, metal, nonmetal. We don't call it molecular. So I'm writing it all out with the units, formula units per mole. And the moles cancel, and you end up with the particles, and that would be 6.02 times 10 to the 24th. Okay? So mole to particle and back. Number 2, we're going to go back. And this is where putting the number in the calculator is going to become correctly is going to become so important. When you divide, if you don't put it in correctly, you'll get the wrong answer. All right, so we are going to be starting with particles in number 2 each time, and we're going back to moles. So we are going to take those particles, 7.1 times 10 to the 24th. I don't know why the superscript is so small. Atoms. And we're going to divide by Avogadro's number. Now you can write it underneath, or you can multiply by the reciprocal. I think it's easier to see the units this way. So this is what you're doing. And then atoms cancel and you end up with moles. All right, that's the way you should be doing this. So 7.1 to the 24th divided by Avogadro's number. And your answer here should be 11.8 moles. All right. Why don't you pause the video and give B and C a try, and then come back and check your answers. I'm going to do them right here. So B, 8.3 times 10 to the 15th molecules this time. I get 1.38 or 1.4 times 10 to the minus 8. So I'm going to write that right here. 1.4 times 10 to the minus 8 moles. So important, guys, as we move into chemistry math, that you put the unit after. Okay, you do a calculation, because if you don't, you are going to be lost when you look at those numbers. All right. C, 6.7 times 10 to the 28th, and I'm just going to do this on the calculator if you don't mind, divided by Avogadro's number. Oops. And I end up with 1.1 times 10 to the 5th moles. All right. So back and forth between particles and moles, you're using Avogadro's number. Now we're going to go back to the notes, and we are going to, first of all, I'm going to get us a nice new page for our next stuff. There we go. And we're going to talk about molar mass a little bit. All right. So here in the notes, I have bookmarked right here at the top of this page a nice PowerPoint that has loads of examples and so on the mole. And it has a lot of interesting little facts about how big that number really is. And then here's another video that you can watch if that will be helpful. This used to be the first time we used the periodic table, so I have referenced that here again. All right, so let's talk a little bit about what the numbers on the periodic table mean. The periodic table contains the information needed to convert between moles and mass. So get your periodic table in front of you. We've already done the nucleus, which involves the atomic number, and of course we still use numbers of valence electrons and things like that off the periodic table, but the number that we have not used yet, and we're going to use now, is this number written as that's not a whole number, and that's the atomic mass. So let's look at nickel. Find nickel. So it should be easier now that you've done some of the language. It says, on my periodic table, it says 58.69 for nickel. So what that means for nickel is that if you compare it to hydrogen, which is what I'm doing here in the notes, it means that nickel, since hydrogen's mass is 1, it means that nickel is almost 59 times heavier than hydrogen. Okay, there are some take-homes about these numbers that I want you to understand. If I want to talk about just one nickel atom, then the mass of a nickel atom in a different unit would be 58.69, and here it is, atomic mass units. All right? If you wanted to take that number for nickel and convert it to grams, this would be your conversion factor. You know, we really don't do that very much. So, the other take-home message about these numbers, and that's what I'm talking about here in the next paragraph, is that I already said it, that nickel was 59 times heavier than hydrogen, which means that they're relative to one another. So what is going on here with these atomic masses is that they represent how much a mole weighs. And we've just got done doing some calculations where every mole has 6.02 times 10 to the 23rd. So 6.02 times 10 to the 23rd atoms of nickel weighs 58.69 grams. So I can take that number from the periodic table for any element, and that number in atomic mass units is how much one atom of that element weighs. Or I can take that number, let's switch to chlorine, 35.453 is what my periodic table says. That means that one atom of chlorine weighs that much in atomic mass units. Or if I take Avogadro's number, or a mole of chlorine, it weighs 35.453 grams. So this is very convenient because it enables me to go between mass and particles through the mole, and it's how we're going to count particles. We can't see them, they're very small, and I think in that presentation there are some interesting facts about how long it would take you to count a mole of something, and how big a mole of avocados is, or apples, or textbooks, or whatever. All right, so we're going to practice this idea. These numbers on the periodic table are all for a mole of each substance. And the way that we're able to do that is that they are a ratio of masses. So let's look at this paragraph right here. Okay. They're called relative masses because they're relative to one another. And in order to compare things, it's easier or necessary that you compare the same number of them. So the masses in the periodic table are relative masses, which means they're a ratio of one mass to the other. When you do this, you end up with the same number of objects. That same number of things is Avogadro's number. Of course, the mass of that pile is going to be really different because of the mass of each particle and the size of the particle. So you'll also see that when you look at, if you go to that presentation, you will see different sizes of moles of things. Like a mole of water is 18 milliliters. I can put a mole of copper into a 25 milliliter graduated cylinder. I can't put a mole of sugar into a 25 milliliter graduated cylinder. It takes up a whole lot more room because it's bigger. All right. So we are going to use the periodic table and the masses on them to go back and forth between moles and mass. All right. So let's put that into practice right before we do. Let's talk about the molar mass of compounds. All right. So since we've talked about compounds and done a lot with formulas, we are a little more comfortable with the fact that this is 2 hydrogens in the water molecule and 1 oxygen. So if I want to know how much that compound weighs, I take 2 times the mass of hydrogen. Do I put it in as this every time? 1.0079? No, I usually do 1.01. Plus the mass of an oxygen atom, which is, on my periodic table, 15.99994. I always put it in at 16. And you add those together, and you get the mass of the compound. All right? So we're going to do the molar mass of a compound. You add them up. So we're going to do not only that, but we're going to do some more practice as well. So let's take this in to our notebook program. All right. So I'm going to draw my little mole chart right here. So we have mole in the middle, particles, which we have already done, back and forth using Avogadro's number. All right. And then our new deal is going to be going back and forth between mass and the mole using the periodic table. Okay. So what is the mass of 15.3 moles of silver? So you are here and you want to go to here. You're going to use the periodic table. Now, this is the other thing. You always put into the calculator first the number you were given. So the first thing you're going to do is put 15.3. So literally it's the number of moles times what's on the periodic table to give you the mass. And then when we go backwards, it'll be the same thing. All right. So 15.3 times, find silver, 107.87. So 15.3 moles times 107.87 grams per mole. All right, and that's going to give you the mass of that quantity of silver. And the answer there is 1.65 times 10 to the third. And in terms of significant figures, I had 3 in my number given, so I'm good there. 1.65 times 10 to the third grams. Always put a unit behind that number. All right, now let's do B, which is for a compound. 3.7 moles of ammonia. That's what NH3 is, times, now I've got to look at the periodic table. Now I want to get rid of moles, so that goes on the bottom. And the grams I get from adding up the molar masses for these 2 elements is going to go on top. So it's going to be, for nitrogen, it is 14.01 plus 3 times the weight of hydrogen. And remember I said I usually use 1.01. All right, so 14.01, I usually put 14 in, plus 3.03 for the 3 hydrogens. So ammonia weighs essentially 17 or 17.04 grams per mole. By adding those up, moles cancel when I multiply them, and I get 63 grams for my answer to B. All right. 4, we're going to go back. We're going to start with a mass. So the first thing you're going to put in the calculator is 250 grams. So 250 divided by the mass of gold from the periodic table, which is 196.97. I'll write out the units in just a second. And I get 1.27 moles as the answer to number 4, A. And I'm going to do a little erasing so it's not quite so crowded. Leave my chart. All right, 4A. All right, go ahead and try B. Add the molar masses up for carbon dioxide. And the first number you're going to put in the calculator is 28 grams times, I'm dividing, but I'm multiplying by the reciprocal, so I can show you the units. All right. So it is going to be 1 mole on top, because that's what I'm trying to get to. And then on the bottom, it's going to be how much carbon dioxide weighs from the periodic table. All right. And if you add those up, you should get 44.01 essentially, which really is pretty much 44. And so 28 divided by 44 gives you 0.64 moles for carbon dioxide. So 4B, 0.64 moles. Okay. Number 5 represents 2 steps because you are starting with mass and you are going to particles. So start here, put the 45 into the calculator first, and I'm going to do it here in dimensional analysis. I will do that for A. 45 grams, want to get rid of grams. That goes on the bottom. I got to go to the mole first, and the way I do that is by dividing by what's on the periodic table for manganese, 54.94. All right, and then that'll get me into moles. So I'm going to do the 2 steps in succession. I want to get out of moles and into particles. So moles has to be on the bottom. How many particles in a mole? Avogadro's number. And this is an element, so it's atoms. It's not one of our elements that comes 2 at a time, and I end up with my numbers of particles. All right. So 45 divided by 50. And then press equal, or do this in parentheses. Oh, no, you don't. This is multiplication. You can do them all together. Times 6.02. To observe order of operations. So 4.93 times 10 to the 23rd atoms. For 5A. All right, go ahead and add up the masses for copper chloride. And I'll do a little erasing while you're working on that. And we'll do it up here, okay? So 60 grams is 60.0. We'll be sure to realize that as when we do our significant figures. Okay, so we've got copper and 2 Cls. Now, copper and chlorine are 2 good examples of not rounding too much on these molar masses. So I am putting in 63.55 plus 35.45 for each of those chlorines. You've got to be careful about rounding. As we get into the math part, this is 134. You can get quite, a little farther from a multiple choice answer on a test, depending on the amount you're rounding, and it depends on your comfort level. I try to be consistent with what I put in, and I'm kind of talking you through that as we do these examples. But just be aware that there will be small differences, because of rounding. So 60 divided by the molar mass to give me moles, and then multiply times Avogadro's number. Now, the nice thing about the calculator is, now this would be, what would the name of this particle be for copper chloride? I see a metal and a nonmetal. It's not a molecule, it's a formula unit. Okay, per mole. And so my number of, so I'm going to go ahead and do the calculation. What I was going to say was often the number that you have in the calculator from the previous operation is still there, so you don't have to clear. That's what I was going to say. Now, in this calculation here, you do have to be aware of your order of operations. When I put 60 divided by 134, I pressed equals, then multiply times Avogadro's number. Or use parentheses. And I get 2.7 times 10 to the 23rd equals 2.7 E23 formula units. Okay? Alrighty. So we've done all the operations using the chart. This is something that you probably want to put on a piece of paper nice and big so that you can, use it, but never lose sight of the units and how to work with the units, because we will be leaving the chart as we get into the more math of our chemistry, and using the dimensional analysis is going to be so helpful in you doing the problems. All right, so this first one is no calculations. It's a thinking question. Without doing any calculations, which of the following contains the most atoms? So if you look at the periodic table, it says that a mole of iron weighs 55, so I'm going to put those numbers in, 55.85. And a gram of boron is 10.81. And a gram of mercury, a mole of mercury, mole of boron was 10.81. A mole of mercury is 200.59. Now these masses represent the same number of particles, 6.02 times 10 to the 23rd. So it takes 200 grams to get up to that number of particles for mercury. It only takes 10 grams to get up to that number for boron. And it takes 55 in between that to get for iron. So it's boron that on a per gram basis has the most atoms. Now if you're a really mathy person and you want to work it out mathematically, you would say 6.02 times, because you want to know atoms, 6.02 times 10 to the 23rd atoms per mole. Atoms per gram is what you want, so times 1 mole, and then divide by the molar masses. So in the case of boron, you're dividing by the 10.81. As this number in the bottom gets larger, the number at the end is going to get smaller. So I'm taking 6.02 and dividing by 10.81, and that's going to give me atoms per gram. So if you want to do it without, with a calculation. Okay, moving on. A helium balloon contains 0.46 grams of helium. How many moles? So where are we starting on our chart? And I'm going to bring my chart back up. There we go. Mass. We're starting up here with mass. Where are we going? Just going to moles. So what I find at this point is students want to use Avogadro's number all the time. You are not on that side of the chart. You're on the mass mole side. So you're going to take that 0.46 grams and you're going to divide by what's on the periodic table for helium. So 1 mole of helium weighs 4.002, so essentially 4. And that's going to be your answer. So 0.46 divided by 4. And I get 0.12 moles. Okay? Next question. Moles to mass. Moles to mass. What is the mass? So you're ending up here, you're starting here. So for each one of these, you're going to be multiplying those moles by what's on the periodic table. So I'm going to go ahead and start filling that in. 6.64 times tungsten. The W comes from its old Latin name of wolfram. All right. Barium. Xenon. And sulfur. All right. And I will put the answers 3A down here. And this is moles. Now, if your calculator is not set up for scientific notation, you saw something like this, okay? Problem with you're using regular notation, as we have learned, it's harder to do the significant figures. B. Even though my calculator for B says times 10 to the first, I usually convert that to regular notation. So that's another question that comes up. When do we know when we have to use scientific notation? There really is no hard and fast rule. I would use it as often as you can. I know that students don't like it. And I wrote a number down without putting the unit. Right, and our last one. And 50.4. Grams. These are grams, not moles. So I put that 50.4 moles in. I was like, that doesn't seem right. Why didn't you stop me? Well, that's one of the disadvantages of not doing this live. All right, so we are mass. We did mass. All right, there we go. Now, number 4. Where are we going? What is the mass? We're going to mass. Where are we starting? We're starting all the way up here with particles. Okay, atom is a particle word, so it's a 2-step problem. Why don't you stop the video and give this a try? You should be ready for this. And then start it back up and check your answer. All right, so I'm going to go ahead and set it up for you. I am got to get out of atoms and get to my central unit, which means it's the mole on top, Avogadro on the bottom. And then I want grams on top, so it's going to be what's on the periodic table, and that's per mole, so that's why those cancel. And this is platinum, PT, so that is 195.1. After I did the first two where I divided, I pressed equals. And you should get 1.59 grams. All right, back to the notes. This will be a good stopping point if you need to take a break. We've got one more practice, okay? And I have not been able to effectively bring these I don't think I can. I'll give it a try, into the notebook program. Oh, it did come in. Sweet. Okay. All right, so we're going to do fill in the table. So we're going to, we have one piece of information, okay? Either moles or mass or number of molecules, and if we have our chart, mass, mole, particles, Avogadro's number on the right, periodic table on the left. All right, so if mole is my central unit, if I'm going to go from mole to molecules, I'm going to be multiplying times Avogadro's number, just like the chart tells me. Back, I'm going to be dividing. Okay? If I go from moles to mass, I'll be multiplying by what's on the PT, the molar mass. If I'm going the other direction, I'll be dividing. Now, the unit you must be in order to do the periodic table is grams, not these. So you're going to have to do a conversion there. So why don't you stop and try this. Put the whole table, fill it out, and then come back. All right. I'm going to start by putting the molar masses for these compounds over here next to them because I know I'm going to need them. Now some of these I have memorized because I've done some of them so many times. All right, so those are my molar masses that I need in order to do the, this direction right here between mass and moles. All right, so I multiply times the molar mass. And then I took those moles that are in the middle and I multiplied times Avogadro's number. Okay. Multiplying moles times Avogadro's number. All right, now before I can do anything with the numbers given to me in these last two rows, I need to convert them to grams. So here's a little practice. I want gram on top. They are 3 spaces apart from one another on our metric chart. So that's 1,000 milligrams. 3 powers of 10 of the smaller in the larger, milligrams is smaller. So this is 0.0238 grams, right? And the opposite for this, grams is smaller, and I want that, so it's on top, 3 spaces apart. So this is 1020 grams. So I need that in order to do my calculations. All right. Now I'm going in the opposite direction than I did earlier. So I'm going to be taking that mass and dividing by the molar mass. So 0.0238 divided by 207. So I've got 1.15 times 10 to the negative 4 moles. Now I can just multiply that times Avogadro's number without doing anything else in the calculator. So 6.92 times 10 to the 19th. Okay. All right, so I've got 8.43 moles in this last one, and then times Avogadro's number. Okay, if this all went too fast for you, then back up to where this table is clear and start over again. That's the advantage to the blended. All right, we are going to get a new blank page for our next. And that finishes up lecture 3.